Okay, so now we're going to start with chemical energetics. We know that we have two types of chemical reactions. Either they are exothermic or they are endothermic. By exothermic, we mean that the energy is given out, and we know that it is denoted by a negative sign because energy is given out and the bonds are being formed, and we know that whenever bonds are formed, energy is given out and it is denoted by a negative sign. In this, the temperature will also increase because heat is given out. Energy given out means it's in the form of heat, so hence the temperature also increases. If we were to make an energy profile diagram for exothermic reactions, if this is the enthalpy or energy, and if this is the reaction progression, so exothermic reaction would somewhat look like this. These are the reactants. They gain activation energy and they form the products. So this is the reactant. This is the activation energy. What is the activation energy? It is the minimum energy that is required so that the reaction can start. And this is the activation energy, and these are the products formed, and this becomes the delta HR, or what we call the enthalpy change of reaction. So you know delta HR stands for the enthalpy change of reaction, and R stands for the reactants. The P here stands for the products, and the EA stands for the activation energy, which is the minimum energy required to start the reaction. Compared to endothermic reactions are the reactions which absorb energy from the surroundings. So there is absorption of energy, and hence that energy is in the form of heat, and since that energy is absorbed, so it decreases the temperature, and since the energy is absorbed, it is denoted by a positive sign. If we were to make the energy profile diagram for an endothermic reaction, it will look like this. Here the bonds are broken, and those bonds are broken by the absorption of energy from the surroundings, and this would look like this. These are the reactants and this is the product. Reactant product, where this whole thing becomes the activation energy, and we can see that the activation energy required here is higher than the activation energy required in an exothermic reaction. It is just this much for an exothermic reaction, whereas it's a lot more in an endothermic reaction. Hence we can say that the exothermic reactions are rather spontaneous because they don't require a lot of activation energy compared to endothermic, which require a lot of activation energy. And this here becomes the delta HR, which is the enthalpy change of reaction. Okay, now so for example, if this is a reaction, calcium carbonate decomposing into calcium oxide plus CO2, this is a reaction, right? So can I call this the enthalpy change of reaction, right? And if I compare it to, let's say, magnesium carbonate decomposing into magnesium oxide plus carbon dioxide, this is also the enthalpy change of reaction. Now and for me to make a viable comparison between the two, I need to make sure that both these reactions occur under standard conditions, and those standard conditions should be applied to all the reactions so the comparison can be made. And these standard conditions are denoted with a phi, and they are 1 atmospheric pressure and 25 degrees Celsius temperature, which can also be called as 298 Kelvin, because we know that 1 degree Celsius plus 273 Kelvin will give us a temperature in Kelvin that happens to be 274. So if you add 273 to a temperature given in Celsius, it will give you the temperature in Kelvin, right? Anyway, so we need to make sure that all the reactions are occurring under standard conditions so that a comparison can be made. Hence, this is how we represent enthalpy change of reaction, that is enthalpy change of reaction occurring under standard conditions. Now, what is standard enthalpy change of reaction? Standard enthalpy change of reaction is just basically when the reactants in their standard state under standard conditions react to form products. right? And this can be enthalpy change, can be endothermic or exothermic. And enthalpy change of reaction, standard enthalpy change of reaction, can be calculated by the enthalpy change of the products minus the enthalpy of the reactants, right? That's how we do it, the products minus the reactants. But the problem here is that you can never know the exact energy or enthalpy of products and reactants. You cannot measure the exact energy of the products and reactants, and hence it is better to say that standard enthalpy change of reaction is equals to enthalpy change of formation of products minus the enthalpy change of formation of the reactants. Hence, we're gonna move on to the next subtopic, which is standard enthalpy change of formation, which can also be written as delta HF with a phi, and that stands for standard enthalpy change of formation. Now, what is standard enthalpy change of formation? It is basically, let's take an example of NaCl, AlCl3, H2SO4, right? What is standard enthalpy change of formation? Enthalpy change of formation is when 1 mole, these should be 1 mole, when 1 mole of product is formed from its constituent elements in their standard state under standard condition. What I mean is, let's look at NaCl. NaCl should be 1 mole because it is being formed, and whatever is being formed should be how much? 1 mole. And it is formed from its constituent elements. If we see NaCl, NaCl comprises of two elements, Na and Cl. What is the standard state of Na? Na exists as a solid. So that's gonna be the reactant along with Cl. Cl does not exist as a monoatomic, however, it is a diatomic gas, right? So Cl2 in its natural state is gaseous. So these combine to form 1 mole of NaCl. We should balance the equation. We have 1 Na on the reactants and 1 Na on the product. However, we have 2 Cls on the reactant and 1 Cl on the product. Hence, we're going to make it half because the product should be how much? 1 mole. And this enthalpy here stands for the enthalpy change of formation. Formation of what? NaCl. Likewise, for AlCl3, it's going to be aluminum solid because we know it's a metal plus Cl2 gas. But now we need 3 moles because we have 3 here. So it's going to be 3 upon 2 because if you do 3 upon 2 times 2, we will get 3 moles, right? And then H2SO4, it will be formed from H2, which exists as a gas, plus sulfur. The natural occurring state of sulfur is S8, solid. But you need 1 sulfur here and you have 8 here. So can I say 1 upon 8? Because 1 upon 8 times 8 will give me 1. Plus oxygen. Oxygen also exists as a gas and you have 4 oxygens here. So you need 2 more to make it balanced. And all of these are going to be enthalpy changes of formation of the respective compounds. Just remember that whenever we are dealing with enthalpy change of formation, the compound being formed should be 1 mole. These guys should all be 1 mole. Let's look at another example for formation and then we move on to enthalpy change of combustion. Let's say C6H12O6, that's glucose. Formation of glucose. The equation for formation of glucose will be carbon in its natural state, which is solid, plus hydrogen, which is H2 gas, plus oxygen, which is also gas. You have 6 carbons here, so it's going to be 6C. You have 12 hydrogen atoms here. You have 2, so it's going to be 6 times 2, which will give you 12. And you have 6 here, 2 here, so 3 times 2 will give you 6. And this becomes the enthalpy change of formation of glucose. So that's how you construct the equations for enthalpy changes of formation. Now, there's also another enthalpy change which is known as the enthalpy change of combustion. Combustion, we all know, is what? Burning in oxygen. Burning in oxygen, if a hydrocarbon burns in oxygen completely, it will give us carbon dioxide and water. If it burns incompletely, it will give us carbon monoxide, right? But we deal with complete combustions. Enthalpy change of combustion can be denoted with in delta HC with a phi. Means it's a standard enthalpy change of combustion. And those standard conditions obviously are 1 atmospheric pressure and 25 degrees Celsius. Now, what is enthalpy change of combustion? A hydrocarbon, when it burns, hydrocarbon means something that has both carbon, and hydrogen. So CXHY, whatever compound it may be, whenever a hydrocarbon burns in oxygen, it will give carbon dioxide and water on complete combustion. Let's assume CH4, methane. It burns in oxygen to give us carbon dioxide and water. Let's take ethene, C2H4. It burns in oxygen to give us carbon dioxide and water. Now, like formation, you had to make sure that the product being formed should be 1 mole. For combustion, you have to make sure that what is undergoing combustion should be what? 1 mole. So if this is 1 mole, you have 1 carbon here, 1 carbon here, carbons are balanced, carbon atoms are balanced. You have 4 hydrogen here, you have 2 here, so you add 2 here, so they become 4 hydrogen atoms. You have 2 oxygen here, and you have 2 twos are 4 and 5 6, so you make it 3. So now this equation is balanced. For ethene, it's C2H4, but this should be 1 mole. So you have 2 carbon atoms here, you have 1 here, so you make a 2 here. You have 4 hydrogens here, and you have 2 here, so it's going to be 2, and you have a total of 2 twos are 4 and 5 6 oxygen atoms, so you're going to add a 3. Now this is a balanced equation, but we have to make sure that whatever is undergoing combustion should be what? 1 mole, right? And this enthalpy change is referred to as enthalpy change of combustion, and this is a combustion of methane, so it's going to be combustion of methane. This here is a combustion of ethene, so this is going to be enthalpy change of combustion of ethene. If just carbon undergoes combustion, obviously since there is no hydrogen here in the reactants, it can't make water, it will just make carbon dioxide. This here can be called enthalpy change of combustion of carbon under standard conditions, because 1 mole of carbon is being burnt in oxygen to give carbon dioxide. This equation right here can also be called as enthalpy change of formation of CO2, because 1 mole of CO2 is being formed from its constituent elements in their standard states. So this equation can both be enthalpy changes of combustion of carbon and formation of carbon dioxide. Likewise, if hydrogen burns in oxygen, it will give water only, because there is no carbon in the reactant, so it can't make carbon dioxide, right? And whatever is burning should be 1 mole. So hydrogen should be 1 mole, and to balance it, you have 2 hydrogen atoms here, you have 2 here, you have 1 oxygen here, but you have 2 here, so make it half. This equation can be called enthalpy change of combustion of hydrogen, and likewise this can also be called enthalpy change of formation of water, because 1 mole of water is being formed here from its constituent elements in their standard states, right? So these equations can interchangeably be used for combustion of hydrogen and formation of water respectively. Now, having said that, knowing what enthalpy change of combustion is, knowing what enthalpy changes of formation is, we'll move on to Hess's law. Now, I will explain Hess's law with respect to a question which is right here that requires you to find out the enthalpy change of formation of propanone right here. This is what you have to find, and the data provided is combustion data of hydrogen, carbon, and propanone, right? So the first step, Now, the first step is to make equations of everything that is provided. Make equations of all the data that is provided. Let's see. Combustion of hydrogen. That means hydrogen is burning in oxygen to give water, not carbon dioxide, because there is no carbon on the reactant side. Again, we balance it. For combustion, we know that whatever is burning should be 1 mole, and that makes oxygen half, right? Now, combustion of carbon. Carbon should be 1 mole because it's undergoing combustion, and when it undergoes combustion, it will only produce carbon dioxide. Then we have combustion of propanone. Propanone is C3H6O. When this burns in oxygen, this will give carbon dioxide and water because it has both carbon and hydrogen. If we balance it, we have 3 carbon atoms here, so it's going to be 3CO2. We have 6 hydrogen atoms here, so it's going to be 3H2O. 3 2s are 6. And we have 3 2s are 6 and 9 oxygen atoms on the product side, but we have 3 here, so if we make 4 2s are 8 and 1 9 oxygen atoms. So we make balanced equations of the data provided. That is the step number 1. That is our step number 1. Then we move on to the second step. That is, what does it require? It requires you to find formation of propanone. And what will be the equation for the formation of propanone? We know that whatever is being formed should be 1 mole from its constituent elements in their standard state. So this element, carbon, is going to be carbon solid plus hydrogen, you know it's a gas, H2 gas, plus oxygen, which is also a gas. You have 3 carbon atoms in propanone, so it's going to be 3C. You have 6 hydrogen atoms, it's going to be 3 2s are 6, and you have 1, so it's going to be a half. This is what you have to find, and the value for this is x because this is what we have to find. The combustion for hydrogen provided here is minus 286. The combustion of carbon provided is minus 394, and combustion of propanone provided is minus 1786. So this is what we do. This is our first step. Then our second step is to make 3 boxes. This is box number 1. This is box number 2. And this right here is box number 3. So this is 1, this is 2, and this is 3. What you do is, whatever you have to find, whichever equation has x in it, you put it in the first 2 boxes. So the third step is put x in the first 2 boxes. So we know that our x lies in this equation right here, which is formation of C3H6O. So I can put it in the first 2 boxes. So it's going to be 3C plus 3H2 plus half O2 becoming C3H6O, and the value for this is x. Now the rest of the 3 equations, that is this one, and this one, you have to put the rest of it in box number 3. So that's the fourth step. Put the rest of the equations in box 3. Now how do you do that? Let's look at the combustion of hydrogen, this equation first. So it is hydrogen plus oxygen becoming H2O. So in box number 1 we do see hydrogen right here, and we also see oxygen. So hydrogen is burning in oxygen to give us H2O. We've been given the value for this as minus 286, but this value is for 1 mole. How many moles do we have here? 3 moles. So can we say minus 286 times 3? Because not 1 mole is undergoing combustion now, 3 moles are undergoing combustion. The value we were provided with was for 1 mole, but how many moles are burning here? 3. So the energy will be thrice as much. Then let's look at the combustion of carbon. Combustion of carbon right here, value for 1 mole. is minus 394, where carbon burns in oxygen to give carbon dioxide. We have carbon here, and we can say this is burning in oxygen to produce carbon dioxide. There's this value provided for 1 mole, but again we see there are 3 moles burning. So can we say minus 394 times 3? Then we look at the last equation, which is the combustion of C3H6O. We see that C3H6O burns in oxygen to give carbon dioxide and water. And we already have carbon dioxide and water in the third box, so we don't really have to write anything. And we know that 1 mole is burning, and the value for that is minus 1786. So this is going to be 1786. This is your Hess cycle. Your fifth step is to determine the start and end box. How do you do that? If you look at an arrow, this is an arrow, this is the tail, and this is the arrowhead, right? So to determine the start and the end box, you have to look at the tail and the arrowheads. The start box is going to be the box where you see maximum number of tails. So if you look at box number 1, there's a tail here, there's a tail here, and there's a tail here. There's also a tail on box number 2, but there's just one tail, right? Right here. There's only one tail facing box number 2. So definitely that doesn't have to be the start. The start is going to be where you have maximum number of tails. So can I call this the start box? The end box is going to be the box where you have maximum number of arrowheads. Let's put these arrowheads with purple, or yeah, purple, no, green. Okay, so this is an arrowhead, this is an arrowhead, this is an arrowhead. You also have one arrowhead here, but you just have one arrowhead facing 2, and then it goes back to 3. So can I conveniently say 3 becomes my end box because it has maximum number of arrowheads facing towards itself? Now, law of thermodynamics says you can go from the start to the end directly. So start to end directly means from 1 to box number 3. So you can go from 1 to 3 directly, or you can go indirectly, that is 1 to 2 and then 2 to 3. They are going to be equal because there is no energy loss. They say that energy is just converted and the value is going to be the same. So whether you go from the start to the end directly, that is from box number 1 to box number 3, whether you go directly, this is direct, or you go indirectly, it's going to be the same. That means it's going to be equal. Let's look at the values for box number 1 to 3. You have this going 1 to 3 and you have this going 1 to 3. So can I write this as minus 394 times 3 plus minus 286 times 3? These both values correspond to box number 1 to 3 directly, and this is equals to going from box number 1 to 2, and the value for that is x, and the value for 2 to 3, which is minus 1786. So can I put that down as x plus minus 1786, and we can find the value for x.